to demonstrate how diagnosis and procedure codes and also explore how these patients can be further clustered into subtypes that can be useful for clinical 2013. So we took the data for this study from the electronic health records of Dan Reed Hospital from November 2010 to January 2017, around for like 610 patients. It's a very small number, but it's a very niche group of patients, so it's difficult to have those patients because it has a very strict inclusion and exclusion criteria for the registration of the integrated practice unit itself. So we, and one thing I would like to mention is that in our group, we are not developing the models and algorithms from scratch, but we are rather focusing on implementing already established state-of-the-art and robust models established in other settings, so then we can replicate them in our settings and modify them according to our needs. So we conducted 2 experiments in this study, and we used different types of RNNs. So in the first experiment, we used convolutional neural networks together with the word-to-vector feature embedding, which was originally developed by Zhao et al. And what this model does is that it takes the diagnosis and procedure codes as an input in the form of text corpus, and the output vectors are produced. And then the word-to-vector model is trained on these sequences, and it learns, it produces arrays of sequences. And then the CNN is trained on these arrays of sequences, which are fed in the model in the form of stacked matrix. And then after the training, the model learns typical predominant representations for these patients, which we clustered them based on different clustering algorithms such as k-means and t-SNE. We'll go to that later. In the second experiment, we used RETAIN, which stands for the reverse time attention model, which is a variant of RNN, and it was originally developed by Edward Choi and colleagues. And it is one of the good models which is better in terms of interpretability, and I'll come to that. So what this model does briefly is that it uses 2 types of RNNs, RNN alpha and RNN beta. It takes the sequence as an input, and then it produces the output. But there are 2 features of this model which is worth mentioning, and that is closely related to how the data is structured in healthcare. So we know that in electronic health records, for each patient, the data is recorded over time, and each time stamp, there are like 2 levels of observation. So one, there's a visit, and at each visit, different activities take place, either labeling of these patients with the different diagnosis or procedure codes and other laboratory investigations. So we can say there's a visit level variable, there is visit level of the data and then variable level. So what this model does is that the RNN alpha takes the visit level weights, and our RNN beta takes the variable level weights, and then they learn from these data. So after pre-processing and cleaning our data, we injected the models with 76 diagnosis and 59 clinical procedures. And in experiment 1, the model, we were able to get salient contributors of the 30-day hospital readmissions for these patients. Just want to mention the 30-day hospital readmission is just by convention, it's taken as a standard in different like healthcare quality operation management context. So those patients who visit the hospital again and get readmitted within 30 days of their previous readmissions, those patients are having 30-day hospital readmissions. So the model identified the most salient contributors, both from the diagnosis and the procedures, and we attained pretty good results in terms of validation and test accuracy. So after the model learned the representations, we clustered these patients based on the learned representations by using t-SNE. And you can see here this visualization, which each cluster represents the subtypes of these patients. And you can see that patients in cluster 1 are mostly distinct from patients in the other clusters. So we further wanted to explore what makes these patients different than the other ones. So we extracted the most commonly occurring events and by using engrams. And as I mentioned before, these patients itself is a very niche group, but from a clinical operations management perspective, it is really important to know the subtypes within these patient groups, because they are so complex. There are multimorbid conditions, other diseases associated with them, and then for a clinician, it is really helpful to know the different types, because each different types have different disease trajectories. So we found that in this cluster, there were patients who had chronic obstructive pulmonary disease, and they went through repeated bronchodilation and spirometry. Similarly, in cluster 2, there were patients who had had kidney transplant, and they went through repeated team visits and team conferences. And this team conference is one of the vital components of the whole intervention, that there's a group of physicians and other healthcare professionals who see these patients in groups. And the third clusters, it was composed of patients who had paroxysmal ventricular tachycardia, and they went through repeated control and reprogramming of the pacemaker. So from the results in the first experiment, we can see that we were able to find the salient contributors of the 30-day hospital readmissions. But as I mentioned, the challenge of interpretability, we were not able to, the model did not quantify these contributors or label them either positive or negative. So that's where the retained model comes into play. And then, because this model not only gives you the overall risk of the final chosen outcome, which could be anything. And in this case, you can see down at the bottom here, the overall score, and each predictor, which is the procedures and diagnosis here, it is assigned a specific contribution scores. And then these scores are added up and put in a softmax function, which gives you the final risk score. And we were also in this model able to attain a good validation and test accuracy, which was slightly better than the original developers of the model. So here's a graphical representation of one of the patients, which the retained model predicted the readmission risk for. And you can see the top, the red there, the 95% overall risk of readmission. And then in this graph, the x-axis shows the time, and the y-axis shows the contributions, which range from negative 0.5 to 1.5. So these, there are different labels for the diagnosis and procedures, and you can see that, for example, here, this pink one, it is ventricular tachycardia, so it contributed 63% to the overall risk of 30-day hospital readmission. And these all contributed positively, and we can see that control and reprogramming of the pacemaker and telemetry monitoring contributed negatively. So in other words, the labels on the top, they increase the risk of readmission by that respective factors, and the one at the bottom, they decrease the risk of readmission. So here's another example of illustration of a patient who had obesity and chronic kidney disease stage 3, together with the other conditions, and most of the preceding events in the clinical history had contributed positively to the the 30-day hospital readmission prediction. So our research both has implications for from a research point of view and in practice. In our study, we were able to, both the models were able to identify the salient predictors, but retain was better to quantify and identify the key contributors to 30-day hospital readmissions. And we were able to identify 3 subtypes within the MCC patients, that is those patients with COPD, kidney transplant, and paroxysmal ventricular tachycardia. And our study also shows that temporal data on ICD codes and procedures valuable for personalized disease management strategies. In terms of practical implications, we believe that our model has the potential to positively influence clinical decisions and optimize resource utilization. And by identifying the key disease patterns, it may enhance a clinician's ability to make optimal care decisions. And it also has the predictive potential to predict both clinical and healthcare operations management outcomes. At this stage, we chose this specific outcome, but in the future, we also intend to include clinical outcomes such as heart failure or myocardial infarction and other outcomes. But at this stage, our main focus is on the healthcare operations management outcomes. And obviously there are like limitations and methodological considerations that we need to, we aim to address in the future. For example, we need to understand our data more from a clinical and pathophysiological point of view. So one example is that these patients have a very long period, because they're chronic patients, so it's a very long time period when they are labeled with these different diagnoses and procedures. So some labels in the past or many years ago might not be very significant in this current time. So we intend to differentiate between prevalent and incident events in the future work and developing our models. And we also intend to include more variables such as laboratory data, medications, and length of stay, and as well as increase the sample size because this was very low. This data was collected almost 1 year ago, but now the patients number at the center is increased, but we also intend to include patients at the overall Stockholm County Council level in the later stages of the project. And eventually we want to develop predictive decision support model for these patients where the physicians at the underwritten hospital can use them in their clinical practice, and also convert this into an interactive analytics tool for this patient group. And your feedback and suggestion during this presentation and after is most welcome. Some of the things just mentioned here, what we are struggling with is that how to minimize selection bias, and also to, there are some new project models which address these issues, like for example, unequal time intervals between the different events, so LSTMs and those models, but we are in the exploratory phases. Thank you very much.
Yeah. Do we have questions? Quite a few. Yes.
Maybe it's how many patients do you think we need for this to be successful? For example, we have about 450 patients per patient. Can you repeat the question? Patient size, like how many patients do you need roughly for this to be?
Well, I don't know that if I know the exact number, but like as I said, like we have 610 patients, and then among those patients we had only 268 patients who had the 30-day hospital admissions. But my understanding is that these new models, the deep architectures, RNNs and CNNs, they are better in attaining good results even if the sample size is low. But I don't know the exact number that what would be the good number. But in the, I didn't mention that, but in the later phases, once we develop the model, we would also validate the results in the clinical setting. So we would then know that if we are able to achieve the good results or not. So,
question?
Very useful, thanks. With the actual patient data set, you mentioned that you have, for example, a long history on a patient. And I wonder, do you use that same patient as many points? Do you try and predict the 30-day readmission at many points for the same patient? Or do you just include them once?
Yeah, we just included them once. Yeah, so and we set up to like the prediction, the observation window and the prediction window for the entire period, but we didn't include them at multiple sites. But I think it's in most of, I don't exactly remember now, but there are multiple, there could be for some patients multiple readmissions, but we, at this point, we only include them at once. Yeah.
Fantastic. I know that you had your finger up first, I think, and then she. Yeah.
I was just going to do a question. Did you try in simple models like an SVM or something? In the first example, there was a negative influence of sleep apnea, which I was just curious why.
Yeah.
Could you just repeat, like in a sentence or two?
The question is if we use other simpler models like SVM and the sleep apnea, as you mentioned, it is negative. To be honest, we didn't use them. We were aware of that, but I think some people would argue that the SVMs in those models are more robust and useful in when you have like simple binary classifications, if I'm not mistaken. But in our case, as I mentioned, that our intentions were to look into the literature and identify like advanced deep learning networks, which is like had obtained good results and accuracy. So we didn't try the SVMs or other things. Yeah. And one thing I want to mention that these results, like for example, the sleep apnea had negative effects. So there is, like as I mentioned, limitations. So some of the results would not make much sense. But at least a clinician and cardiologist in our group, from a practical point, these clusters made good sense that, okay, patients with COPD and other conditions were more likely to be readmitted. But still, it needs improvement so that the results can be interpreted more accurately and implemented in practice. Yeah. Please, Sonia.
Thank you. I was wondering about the text corpus and the verbatim aspects of your input. So, in the cell part of the input, that otherwise was text corpus, does it mean that you treated text notes by doctors separately, or was it comments before was it patient's own words, or what was?
Yeah, the diagnosis and the procedures themselves serve as the words and the text corpus, so each one. So we didn't use free text.
So no free text, but just...
Exactly, yeah, the labels of diagnosis and procedures, yeah.
And then you treated them as special words and the 5 words.
Exactly, yeah.
Okay.
Yeah.
And then you had it.
I had the same question.
Ah, so here we go. It's a cluster of
Yeah,
thoughts.
yeah.
Yep.
Did you consider any other approaches like autoencoders or CNNs to capture the facial representation?
Yes, I think, as I said, like it's just the beginning, so we will definitely consider autoencoders and other. As I said, like one of the target for me is the LSTM, much more advanced, like time-aware LSTMs. Now they have come like some researchers. Yeah, sorry.
I saw some. Oh yeah, yeah.
Sorry, can you speak a little louder? Sorry, so that I can hear. Yeah.
Yeah, shout.
All of your pictures are like binary pictures now, yes? Because it's like we don't have any bad results, right? It's like that if patient has the IJCAI code or difficulty texting and HR, so you change to binary data.
Can you quickly repeat?
Sorry, you mean that if we change they are binary, but I'm not sure if the models treat them as binary because it takes them into like sequential order, and they're, yeah.
So then my question is that, so one is that you usually produce a prediction from mathematics, and then the classification that you showed, which model then you use for that classification?
For the classification, we used k-means and other like t-SNE, the t-SNE algorithms for classification. So the model learns the vector representations for these patients after the learning. And then, like, I'm a physician by background and I'm not very good at the technical details, but at least my understanding is that when it learns the representation, so it lies in the high dimensional space. So these algorithms are used to cluster them based on those spatial positions. So we used many algorithms to cluster them to identify which ones are the closest matches with each other. So, yeah. I hope that answers.
Great. Okay, so I think we should close this here. Thanks, Rafik, again.
Thank you very much.
Yeah. I invite the next speaker forward. These were very good questions. Thanks. So, just while you edit. It's just worth noting, so Rafik is one of my PhD students, and we're continuing this type of work at Karolinska now quite heavily, which is very interesting. So I remind everyone it's a workshop also, right? So keep these discussions and everything flowing during the breaks and so on too. Oh, you're there. Fantastic. Okay, so the next talk will actually be a video, but I think you will give a quick introduction. Why cool? Yes.
Due to the Yaozhu and the Xiaoliang funds visa have some problems, and they can't be here to show their work, and then they record a video and ask me to create a video for you. And if you have any question, you can send the email to ask them, and then I will create a video.
Okay. Thanks.
Now, ladies and gentlemen, we are glad to introduce our paper.
Sorry. Excuse me.
Does it not work? One second. Technician is just here. Okay, maybe we do it this way.
Intensive care unit is a rescue. Now, ladies and gentlemen, we are glad to introduce our paper, Predicting ICU Mortality by Supervised Bidirectional LSTM Networks. In this paper, we propose a novel ICU mortality prediction algorithm combining bidirectional LSTM model with supervised learning. We are going to present our work in 3 parts. First, introduction and related works. Intensive care unit is a rescue center for critically ill patients, which provides the utmost service to reduce death in bed events. And mortality prediction in ICU is considered as one of critical steps for the treatment of patients with serious condition in ICU, which in fact assess the severity of patient's illness. Accurate ICU mortality prediction can not only give clinicians a better and earlier sense of which patients are likely to get worse, but also facilitates the efficient allocation of hospital resources. To assess the mortality risk of patients in ICU, there are several classic scoring methods, such as SAPS and a patch. However, it is well known that these scores are limited to a few fixed indicators, which could make it very difficult to accurately reflect the dynamic evolution of patient size in ICU. Machine learning technology has been widely utilized in statistical analysis. The work in Citation 1 achieves a high score in mortality prediction challenge by using support vector machine classifiers. Later, the authors in Citation 2 came up with the CHISC classification algorithm, which is designed to address the imbalance problem in binary classification. More recently, deep neural networks are utilized to learn from the sequence data and able to grasp the long-term dependence of time series data, such as citation 3 and 4. So our work aims to make better use of the strong learning ability of deep neural networks to capture the fluctuations in time series variables and to achieve higher accuracy of mortality prediction in ICU. And then let's look at data sets we utilized and our algorithm. The mortality prediction in the ICU essentially evaluates the risk of the death based on the specific patient's current physiological condition, so that the doctor can take appropriate care. Even the clinical experienced doctor's patient's physiological states during the first 48 hours in the ICU could profoundly influence his or her clinical trends within the next 30 days. Thus, as the caution shows, we divided the prediction in 2 categories. The first class, death in ICU within 30 days, and the second class, death in ICU exceeding 30 days or survival in ICU. In other words, the first type of patients requires more monitoring and care services than those of the second type. The ICU data we employ are from the PhysioNet Computing in Cardiologic Challenge 2012. There are 4,000 patients and records for each patient consist of 2 parts, as shown general descriptors and time series data. We perform the basic statistics on general descriptors, including patients' basic informations. The preliminary observations are described above. We further illustrate the 48-hour time series data between two patients. Patient A was stayed in ICU within 30 days, while patient B survived in the ICU. We selected two high-frequency variables, HR, heart rate, and GCS, for comparison. For example, the fluctuation range of patient A's heart rate is relatively larger, showing an obvious downward trend at the same time, while patient B's heart rate was fluctuated within the normal range. In addition, GCS of patient A has a big drop to below 10 at 6 o'clock p.m., whereas GCS of patient B remains stable within 48 hours. So the overall framework of the ICU mortality prediction model is presented above. First, we pre-process the datasets to get time series vectors and labels for each patient. Second, time series vectors were used as inputs to the supervised bidirectional LSTM model, and we will get a prediction of 0 or 1 by a binary classifier. Finally, the loss is calculated by comparing the predicted value with the true label to train model parameters. We recorded 34 time series variables about the vital signs of the patients with a 1 hour time interval. That is to say, there are at most 48 records in 48 hours for the individual variables. Specifically, 3 data pre-processing steps are shown above. First, data simplification. Second, data completion. And last, data normalization. So, the time series information for each patient is represented by a 34 multiply 48 matrix. In recurrent neural networks, long short-term memory is a relatively more efficient structure. For each patient, his or her physical condition at time t is affected by the previous illness state. Clearly, the abnormally fluctuating time series data in the model require more attention than the normal stable values. From this point of view, memory and forgetting mechanisms are very important to the prediction model. However, this structure limited complete understanding of the characteristics of all time series data. So how about bidirectional LSTM? In fact, bidirectional LSTM consists of forward and backward LSTM structure, which could avoid the blindness that propagation in unidirectional way may cause. As a result, BILSTM is employed to process the input data to reflect the fluctuation of patient's illness condition, as it is more capable of sensitively capturing the changes of patients' physical signs than unidirectional LSTM models. In a simplest bidirectional LSTM recurrent neural network, there is only one output per recurrent module of the hidden layer. When the gradients backpropagate, the entire module calculates the loss value only at the last step. In contrast, a recurrent module can actually be unfolded into multiple modules, each part of which corresponds to a certain moment of the input. Thus, every step can generate output respectively. As for the calculation of the loss value, we apply a supervision technique. The supervision technique here has some advantages. First, it is the local state that affects outcome for the mortality prediction. And grabbing characteristics of local state is exactly what the supervision technique is good at. And second, the supervision technique shows the ordered incremental importance for all time steps, which is consistent with the trend of patient states. Third, supervision technique improves the loss value in recurrent model to make the model effectively handle the long sequence problem. In part 3, we introduce our experimental results. We performed the experiments on 4,000 cases of the PhysioNet dataset with 3,200 patients as the training set and the remaining 800 as the test set. Some experimental setting details are demonstrated below. As the prediction of mortality is a binary classification problem, we choose precision recall F1 and AUC to evaluate our model and compare with baselines. AUC characterizes the ability of the classifier to rank positive samples in front of negative samples. The greater the value of AUC is, the better the effect of classification achieves. We compare our BISTM-ST model with these baselines. We can see clearly from table that the bidirectional STM model with supervised learning technique, that is BISTM-ST, outperforms baselines in general. It is noteworthy that our model performs better than bidirectional LSTM model with attention mechanism. The reason is that, in contrast to the attention mechanism, the supervision technique could supervise each step in reasonable order so that the model can learn features and predict more effectively. Meanwhile, the attention mechanism lacks of attention to local features during the time steps. In addition, the supervision technique is more suitable for mortality prediction because it can better deal with the long sequence problem like the time series data of 48 hours. We also selected the sequence data of the first 24 hours and the first 36 hours after the patient was admitted into the ICU, and the mortality prediction is carried out with the bidirectional LSTM with supervision technique model. The prediction accuracy of BISTM-ST 36 hours and the 48 hours is almost identical. Specifically, the model with 36-hour data even exceeds with 48-hour data on record. As a result, we could use 36 hours of time series data instead of 48 hours, so as to give clinicians an earlier sense of which patients will require critical targeted treatments. Okay, let's make a conclusion. In this paper, we proposed a novel mortality prediction algorithm in ICU. Our experimental results demonstrated that the bidirectional LSTM model with supervised learning mechanism outperforms all other baseline methods. The significance of novel prediction model includes: first, By effectively capturing fluctuations in time series variables, it could give clinicians an earlier sense of the patient's mortality status. And the second, it could be used to help hospitals to allocate ICU resources more efficiently. In the future, we hope a real-world ICU dataset will be employed to evaluate and improve our model. That is what about this paper. If you need more details, please contact us by emails. Thank you.
Okay, thank you. Greetings to, I guess, China, right? Yeah. So my suggestion is in this case that if you have specific questions, it might make sense then to come to you for the authors to get back. Otherwise, I would now suggest to invite the next speaker and come forward. Do we have? Fantastic. Yes. Yeah. Okay, so the next speaker is Sadiq Sani, and the topic is matching networks for personalized human activity recognition. So thanks, Sadiq.
Good afternoon, everyone. And today I'll be talking about personalization in the context of human activity recognition models. So first of all, as a background, what is human activity recognition? So this is the computational task of recognizing human activity from sensor data. So a lot of sensors are used for this task. They include video recording and environmental sensors and wearable sensors. For the context of this work, I'll be focusing on wearable sensors. So human activity recognition has many important applications in healthcare and fitness. The background for this work is a project called SelfBack, where we are developing a system to improve self-management of low back pain. And the importance of physical activity for patients with low back pain is the fact that they get given advice to remain physically active, to maintain moderate levels of physical activity. But also for people with extreme low back pain, they get given advice to avoid maybe high intensity physical activity. So we'd like to monitor this in order to be able to determine that they are adhering to the advice that they're given. So, of course, human activity recognition is typically modeled as a machine learning task. We take continuous sensor data. So in this case, it's a triaxial accelerometer, which measures acceleration in three-dimensional space. It gives us continuous time series data, which we process to extract features. So these are independent identically distributed features, which are used to train a classifier. And also we use that to get a prediction from the classifier. So this brings us to an important consideration in this regard, which is how do you train these models? So the traditional way this is done is to get a sample of people who are sort of representative of the target population of the users of this application. And you get them to where these sensors, they do a number of activities, which are think activities like sitting, standing, running, and then you build a model using the data from all these users. However, so the advantage of this, of course, is that you've got one system which can be used by many users, right? So you develop one system which targets the entire population. And also, of course, you build this model when you develop your system, so once you deploy it, it's ready to use. But the major disadvantage of this is accuracy. So previously in literature, the tests between building a model from a sample population and building individualized models for individuals we've seen differences in accuracy that ranges from 6.9% to up to 38.7%. So of course, a model which is non-personalized tends to miss out individual differences in the way people do their activities, which can be attributed to possibly differences in gait, posture, and maybe gender and age, etc. So at the extreme end is to develop subject-dependent or personalized models. So for each target individual that you want to use your system, you develop a model specific for that person. But of course, this is theoretical because it's not feasible in the real world. Because how do you build a model for each individual user of your application? You would require that user to provide you with training data, and that is simply not feasible because a user cannot be expected to provide sufficient data to train an accurate model. So of course, our proposal is to have some sort of hybrid approach where you sort of get the user to provide you with just little data. So for example, just 1 minute of data for each activity that you wish to recognize. And then you can use that to bootstrap a model. So our proposal for this is to use matching networks. Matching networks are a neural network architecture that were originally introduced for the task of one-shot learning. And one-shot learning is learning from as little as just one example. So matching networks do this by reusing the class label of the most similar instance in a given support set. So your support set would contain at least one example per class that you wish to classify, and you can reuse that to make your prediction. So, and an important feature of matching networks is that they use metric learning to learn feature representations that maximize classification accuracy, giving you a similarity metric. So I'll illustrate this in the next slide. So this is what you want to do. You have a test example. So some sensor data which you want to classify. You don't know what activity this is. You have a support set. So like I mentioned, your support set contains one or more examples per class, and that's what you need. You have this parametric function called f theta, which in this case is a neural network. And this function produces feature representations for each of these examples. So once you do that, you get feature representations. For the support set, of course, you know what the activity labels are. You pass these through an attention mechanism. The attention mechanism simply just computes the similarity between the test example and all the examples in the feature set, in your support set. And then it converts this to prediction, to probabilities using just a softmax operation. So you have a vector of probabilities, which is the same dimension as the number of instances you have in your support set. You do the argmax, so you take the maximum probability. And so in this case, it's the third example, and the third example is walking, so you make a prediction that the person is walking. So as you can see, the entire the classification from a matching network is completely dependent on the support set. That's all it uses to make a prediction. So of course, our expectation is that for personalization, the end user will be happy to give us a few examples of each type of activity we want to recognize. And we can use this to make predictions for that target user. So in that case, the model is sort of personalized to that individual user. So how do you train a matching network to do this task? So we organize our training in a similar way. So we start off with a training set of multiple users, but we take just one user to begin with. So we organize our training per user. So let's say we have this user called Bob. We sample from Bob an instance X, which is the test instance that we want to classify, which has the label Y1, and the support set S1, which is, again, contains at least one example per type of activity. We pass these through our matching network. We obtain our feature embeddings, and we pass these through our attention mechanism. We get our vector of probabilities. We make a prediction based on that, and we compare that with our ground truth, so our Y label. We compute the loss, and then we backpropagate and update our weights. So we sample for this user Bob M times, so M could be any number. In our experiments, we did 500 times. So 500 times we sample an instance with a class label and a support set. and we backpropagate all this while. So once we're done with Bob, we move on to Alice, another user, and we repeat the same process for Alice, and then Richard, and on until we exhaust all the users in our training set. So to move on to evaluation, evaluation is done on a data set of about 50 people. Like I said, we use a triaxial accelerometer, which is one on the wrist. We have 9 activity classes, and these are the activities. For walking, we include the walking at 3 different paces, so slow, normal, and fast. Like I said, particularly for softback, we're interested in knowing the intensity of the activity. So each activity we've got 3 minutes of data for each activity. We take the first minute, so the first 60 seconds, to sort of mimic this user-provided examples, which we use to create our support set. We use the subsequent 2 minutes for testing, and we do a holdout validation, and we report macro average F1 score. So we compare our matching network against 3 baseline approaches. So one is a standard key nearest neighbor approach, because again, like I said, the matching networks sort of behave in a similar way to a KNN algorithm. We compare this against support vector machines and also a feed-forward neural network, which is exactly like the embedding we use for the matching network, except that it has an output layer, which is the number of classes, and a softmax classification output. So these are the results we got. As you can clearly see, the matching network outperforms all the other approaches by a minimum of at least 6%. So this is a huge improvement, and this shows that the personalization is important, and the matching network is able to build a personalized model for the user. And again, like I mentioned, once we train the matching network, all we use at test time is just a support set that's actually provided by the user. So all classification happens using this support set. So in conclusion, we presented matching networks for the task of personalized human activity recognition. We have shown that this is actually good. It produces at least 6% improvement. And this approach is actually feasible for real-world application, because once you build the model, once you've trained the model, you don't need to rebuild it again. You just need to provide a support set, and this support set can be provided dynamically at runtime. If the context of the user changes, you just provide a new support set, and the system continues to work. And that is me. Thank you.
Thank you. Do we have questions? Yep.
Fully understand how the matching network works. So the input is the raw data from, for example, gate, other things.
Yes.
And,
so
okay, and does the attention, so then you do convolution, and does the attention also treats because they might be type shifted, so if you have gates, it might look like a sinusoid, but you don't know when you started.
Yes, so the embedding function, of course, abstracts from the raw representation, from the raw data. So it goes through a feature embedding, and the matching network compares the output of that. So it's the feature vectors you get from that.
Time for one more quick question? No, not now. Thanks so much. Thanks again. The next speaker, Jeff Drews, I believe. Yep. Okay, so the next speaker is Jeff Drews, predicting observable and occult injuries and trauma patients from sparse measurements. Thanks.
Okay. Okay, so first thing, let me apologize for my. Not getting anything here. Thank you. Appreciate it.
Sorry, I haven't had this issue before. Is anyone familiar with this particular?
Yeah.
You just go.
Now your home screen. Okay. We go back into the space. But we've got to look at that. That's the home screen.
Okay.
Eight simple screens.
Yeah.
Nice space in there.
So present that. Okay, so thank you. Sorry. I was going to just read this very slowly for 2 minutes anyway, so we're totally fine. Okay, so this is predicting observable and occult injuries in trauma patients from sparse measurements. So quick note on what sparse measurements mean. Sparse measurements mean this is only a couple of measurements from the patient. This isn't a high resolution scan. This is just looking at things like heart rate, breathing rate, Glasgow Coma score. So what can we do with just a minimal amount of information for a patient? This is our team. Just a quick shout out to Dr. Rishi Kundi, our subject matter expert in vascular trauma. An overview is we want to improve the overall survival rates for trauma victims. And we want to do this by assisting first responders in giving them an accurate diagnosis tool that they can use in the field, and they can do so without information from expensive diagnostics equipment or from advice from a highly trained medical professional. Okay, so the problem is that we have about 10% of all deaths can be attributed to traumatic injury. And in the cases of, in a combat setting, for example, almost a quarter of these are survivable. And out of these survivable injuries, hemorrhages are a major killer among these trauma victims. And so if we can find out a mechanism to help us out identify accurately vascular injuries such as things that lead to hemorrhaging, we can overall improve survivability of injuries. And then also another problem is that first responders may not have a whole lot of skill. They aren't going to have this super deep knowledge base that doctors are going to have, or access to even the equipment in some scenarios. So another problem is that economically developing countries, also natural disasters areas, as well as combat scenes, people aren't going to have access to equipment either. So how can we have a tool that reaches everybody? Fortunately, a lot of people have cell phones. Even in very poor places, people have access to cell phones. So how can we exploit this fact that cell phones are everywhere to help trauma victims? So the idea is that we want to assist these providers by exploiting the patterns that emerge in large electronic health records to train machine learning algorithms that are delivered to a cell phone that can help these first responders without the access to the sophisticated diagnostic equipment. Okay, so we're almost caught up to speed now, so excuse that, it was pretty rapid. So what do we use to data? So the key element here is these are data-driven models. We need data to populate them. So we use trauma patient data from the Cowley Shock Trauma Center from University of Maryland. We have 2,643 users where we have 774 injuries that we're trying to perform injuries over. Some of them have an extremely low number of examples, like 2 or 3 of some odd injuries. So we chose the 34 top injuries that were of most interest to our subject matter experts, which were vascular surgeons that said, hey, we see these things all the time. They're very, very problematic. Let's look at these. And out of those, the ones that we, out of those injuries, primarily those were vascular injuries, things related to bleeding, and also solid organ injuries, which would lead to death or death further down the road if people weren't properly diagnosed. To touch base again on the features we used, these again are the sparse measurements. These are things like breathing rate, heart rate, Glasgow coma score, approximate method of injury, looking at leg, happen in your upper thorax, things like that. Also, mechanism of injury, penetrating, crushing, blunt. And the important thing about these features is that it doesn't take a highly skilled medical professional to pick these out. A person with just a little bit of training, such as first responders, can pick all these and then populate them into a cell phone app pretty readily. To validate our data, we use 5-fold cross-validation for all of these. Okay, so we used once we had this data, we populated and trained a variety of models. We used support vector machine with RBF kernel, decision trees, neural networks, random forests. And out of all of these, the decision trees and the neural networks showed the most promise in terms of creating good results, so we chose to go with those. This is an example of our model, which is trying to identify an injury to a femoral artery in the leg. You can see at the top branch of our decision tree is there observed extremity injury in the lower part of the body? You want to see it's yes. So obviously this is a good first sanity check to see what's most important in determining this particular injury. Another appealing element of decision trees is, if anyone knows a lot about machine learning algorithms in healthcare, they need to be explainable. If you pass someone a giant neural network, they're not going to be able to make much sense out of looking at its activation functions and presuming they know what's going on. Decision trees, they do pretty good, and they also perform comparably well to neural networks. So we chose them for our extensive study. Here we have all of the results for 12 of the injuries that we saw. The cool thing about these is doing a little bit of background search with our subject matter experts is that these are kind of comparable that what some physicians can get with like regular x-rays with now without CT scans, you can get incredibly high accuracy and precision, but pretty comparable to what they can get with some regular diagnostic tools. And these are with just looking at a few features, 30 features that are derived from simply observable things, the features I mentioned, breathing rate, heart rate, things like that. So next steps, what do we need to do? We want to look at larger data sets so we can populate these models, perhaps build more sophisticated neural networks that have a higher modeling capacity. The higher modeling capacity requires a larger training set, so we can look at larger data sets like the Shock Trauma Center has over like 1 million data entries we're looking at obtaining. We want to look at more classifiers. For example, noisy OR networks are pretty cool. We're looking at exploring those. Our cell app is done in terms of a mock-up. It's not running our classifiers, but it actually does, you can populate a user, you can input the features, it's almost complete. A cool thing that is out now is TensorFlow is actually runnable on Android, which has a pretty high-powered GPU. So once we have these sophisticated deep learning models, we can actually run them on any Android phone without any issues computationally. A user study, so very important to this is it actually going to work according to first responders? We have something set up with MedStar where they're going to look at how it functions, looking at what we get from it, and make suggestions as to what we can do in the future. Also, and I would appreciate any feedback, is precision and recall. You can train these classifiers to either be better at precision or recall, whatever you need to do. Also, our UI completed by our human factors team, so it's maximally efficient for conveying whatever information we want to. With that, thank you for your time, and I'll answer any quick questions if we have them.
Do we have questions?
Sure.
Shoot. Yeah.
So you use the neural network for the higher management data?
We use decision trees and neural networks. We kind of play with both. Yes? It's a good question. Always important. So we do. With the lower data sets, the lower injuries, we do reproduction of samples, so we have ultimately a balanced data set. We then, with our full validation, we only have a couple in there, and we confirmed that it wasn't overfit by doing random perturbations to different members of the different features in the data to make sure the results aren't varying wildly. Because if they were highly tuned overfit to the lower data samples, then they would just get wrong if any little thing changed. But we confirmed that by random perturbation of features. Yeah.
Great. Another one here, yeah?
Yes. Oh, by touching someone. Okay. So, well, this is actually the heart rate was recorded in the data. So we have all these features were just given. So I didn't ask the nurse, so I'm not sure what that would be. So yeah.
Okay. No worries. Cool. Thank you.
Thank you.
Great. So then I would ask the next speaker on stage, and it wouldn't be, please go, It wouldn't be a health workshop if we don't take a few seconds or maybe half a minute for us to all stand up. We had 1 hour of sitting down, so please all stand up, stretch a little bit, exactly. We have half a minute, exchange a little bit. I think it's our dean at Karolinska does that very often. He's a physiologist, so he tries to, he even has exercises, but I'm not sure. I know it gets the blood flowing and stuff, so excellent.
Nobody sleeps.
Yeah, no one is sleeping. That's right. Everybody's passed out, with the heat. Good. Fantastic. Thanks. So the next speaker, is Fernando Andriotti from the University of Oxford. And your talk is on
visualizing convolutional neural networks decisions in automated sleep staging.
Excellent. Great.
So,
thanks.
I'm in the Institute of Biomedical Engineering at Oxford. And as Jeff also briefly mentioned, it is very important in medical applications that we try to understand what these kind of methods are doing. And here I'm going to present it about sleep staging, so specific to the sleep scoring task. So sleep is related to mental health, and there are various associations between, for example, mental health conditions such as depression. People tend to have sleep disorders, or even people that have some sleep disorders might be a good predictor of more serious neurological conditions later on, such as dementia. So nowadays, what we do when somebody's suspected to have a sleep problem, so they do a polysomnography, which entails putting several sensors to the person, such as electroencephalogram, electrooculogram, which is the eye movements, electromyography, which is muscular tone, amongst others. And it is very very cumbersome. So, and not only that is cumbersome, also the analysis of it is very cumbersome, where some sleep technician has to sit there and look at various sleep epochs and annotate for events and things like that. So this is of course very expensive, time-consuming, tedious, and there is a huge intra-rate of variability. That's why we aim for automated sleep staging, at least to help out in this very objective small task. Well, I'm aware that the conference has various topics, so I'll just go quickly through what's actually sleep scoring so that everybody follows. So there are several guidelines on how to score sleep. The American Academy of Sleep Medicine, for example, is one of them, is the one I use here. So it looks at every 30-second epochs of sleep. It classifies into 5 classes based on predefined frequency bands, such as the delta, theta, alpha, and so on. So, and here are some of the sleep states. So, for of course, wakefulness. There is usually some alpha activity involved in the EEG, the EOG. So there are eye movements, and the EMG. Of course, we have some muscular tone. The N1, 2, 3 are non-REM states or non-rapid eye movement states. And they all have their characteristics. There are some norms. And 2, for example, is very different from the other ones that you might expect some patterns on the EEG that look like this. So there are K complexes and sleep spindles. They're very particular of this stage. And the last one is rapid eye movement, where there is some lower alpha. Of course, there is eye movement, and the muscular tones should be at its lowest. Beneath each stage here, you can see just the predominance of it. So it's an imbalance problem as well. So N2 is pretty much 50% of sleep. And here is what the hypnogram looks like. So how these sleep stages flow through time. So on the top, there is a healthy subject. So you see how the sleep cycles go. And beneath, there is a patient with REM behavior disorder. So you can see that his sleep is very fragmented. Traditional methods for dealing with automated sleep staging, of course, is the general signal processing chain, so feature extraction, feature selection, classification. And typical feature extraction methods are statistical analysis, entropy measures, power of some frequency bands. And of course, they use classifiers such as FEM or random forest. And if you want to get the temporal idea of these transitions of sleep in the hypnogram, you might use some HMM or something like that. There have been some deep learning studies as well in the last couple of years. The first one, Langvist proposes using deep belief networks for generating unsupervised features. Some others propose convolutional neural network or recurrent neural network specific for sleep staging as well. And others use transfer learning from image models, trying to apply it for sleep. I'll talk a little bit about that later on. Here are some examples of the networks they propose. So the first and the last one, for example, you just use one lead EEG, whereas the middle one use multiple leads of EEG and EMG and EOG, so different signals. And they're all fairly simple. They're not too deep, I would say. So the idea of our work is to use as few leads as possible. That because at our lab we aim to try to make this portable so that we can maybe give the patient a wearable device and collect through several days. So we would like to reduce the number we have, but we also would like to have all the signals. So EEG, EOG, and EMG. Here we propose a very simple convolutional neural network we trained from scratch. And we try to visualize the network's weights in each channel. So each input channel we have. And the idea is that we could allow some more interaction between the clinicians and the eventually. And the cliche of opening the back books. So here's the materials that we use in this work. So we use the openly available data set, the MAS data set, which is Montreal Archive for Sleep Studies. It contains 200 healthy subjects. And they have several leads. So here we picked up 3, so one EEG, which is a central derivation, one EOG, so right minus left, EMG from the chin. And we use the AAS rules that I said, 5 sleep stages. I mentioned there is a class imbalance, so before using the data, I just balanced them out by undersampling to the minority class. And then, so since we want to visualize it, I thought maybe we should do the time frequency transform because EEG is very based on the frequency analysis of the signal itself. So the input is usually the raw 30-second epochs of each signal. So we transform each one of these using the continuous wavelet transform, using the Morlet wavelet, which has been proposed in different works. And we end up with these images or scalograms, which is 30. So we picked up 30 scales, and it's 300 because we kind of averaging time a little bit just to compress a little bit. And we do channel-wise and sample-wise normalization, which is typical for neural nets. So here's an example of how the scalograms kind of look like for EEG, EOG, EMG. The EMG, here is some ECG artifacts on it. And one thing to pay attention to is that the EMG usually you high pass it to after 10 hertz. So we will only be paying attention to the upper part of this plot here, or the EMG exclusively. Well, the network, as I mentioned, is very simple. So we just propose a network which has two 2 convolutional layers, just to kind of dim down this dimension. And then we use this inception light block, which does convolutions in 3x3, 5x5, and 7x7 windows. So yes, this network is extensible. So it was just a proof of concept at first. So there are several methods for post-hoc visualization. That means that after you train the network, you kind of look at the network and try to figure out what the weights do for a specific example. There, roughly said, there are 2 main types of algorithms. So there are gradient-based ones, which search for an image that maximizes the output of the model. 2 examples are guided backpropagation and deconv nets. And there is also sensitivity analysis, which is quite popular. It generates this kind of heat maps, but it's usually based on the latter layers and how the change of the pixels might lead to an effect on the last layers. So the first one looks kind of often unnatural, produce unnatural images. So and a lot of people try to do some regularizations to try to improve it. And the last one is kind of merge all the channels and do like a blob of heat map. So there have been some studies regarding sleep and try to visualize this in the last couple of years, 2 years, or last year. The first one, Villamala did using short-time Fourier transform, and he applied something that looks like sensitivity maps. The second one did use the wavelet for that, but he didn't do much of a visualization, but he did for sleep staging apply the two-dimensional network onto that. And the third one, I think, is here, and he might correct it. There you go. And he might correct it if I'm wrong. But you've done some correlation analysis on multiple leads of EEG, and you try to focus on which parts of the brain this feature is present, roughly said. Okay, so that's how this the method that I picked look like. So it's the guided breadcrumb. So it merges the best of these 2 different streams. So it uses guided backpropagation as well as CAM, which is class activation maps, which is one type of sensitivity map, and just does the dot product of these both, trying to get a better localization of these features. So it's been proposed last year. So and it works, as I mentioned, it works on the pre-trained model, so you don't have to do any training later on. So here's the results of training. While I was training my model, I just wanted to check if it's doing sleep staging properly, and there's a tenfold cross-validation. As you can see, the N1 state is the problematic one as usual, because it kind of looks like wake at some time and N2. So that overall accuracy is around 75%, and a Cohen kappa of 0.69. So moving on to the visualization. So in the first row, so the labels are here on the right side. So the first row is the scaleogram, how it looked like. The second one is the guided backdrop, and the third one, the method we use here. And on the first column is EEG, the second EOG, and the third EMG. So here is a episode of wake. So we see that there is some alpha frequency on the EEG, and it looks like the network decrease. So the more close to yellow, that means that the network puts more weight onto it for this particular example. So it looks like it doesn't use much of the alpha wave for detecting here, at least on wake, as wake. EOG, there's eye movement, so it's trying to focus on different parts of the frequency domain. And as I mentioned here, the EMG will just focus on this upper part here, but there is some movement. There's nothing too much to see here. So that's the second example. That's the N2. As I mentioned, there are very particular patterns that occur on N2, the K complexes and splines. So we can see here that these patterns here on the EEG, and we assume they are K complexes and splines. And as you can see on the down there on the breadcrumb, it really focuses around this frequency, which is pretty much spline. So it's the range of the spline, and sometimes it goes down to lower frequency where K complexes are. And something very similar on the EOG. And here's how this epoch looks like. So as you can see, there are some K complexes indeed, which occur in these regions here. And also there are some splines everywhere. So the network kind of looks like it's picking that up. And this third example is REM. So REM is also sometimes is known for having like lower alpha activity, so 8 to 10 hertz, let's say. And the network seems to use REM for this bit at least of the alpha for detecting REM. And EOG is the same as before. It's kind of spread out everywhere as you expect. So we propose a very simple network. It does sleep scoring, although it's, we are aware of, and we have done previous works that have shown that RNNs also perform really well and perform better than them because they take into consideration this sleep transition between states. We could evaluate the using more signals such as EEG, ACG, or respiration. The problem with these visualization methods, and I think we've seen a couple of times at the conference, is that there is really no ground truth. So they're merely qualitative in many cases, and they're very specific to one example. So another problem is that they're very recent. So there's a lot of works happening in this area, and every year there are several new methods to it. So if you want to use RNNs, you could also do some attention to try to visualize this importance as well. And then of course, this is just a very specific task of sleep scoring, and that's just part of a bigger problem, which is really diagnosing some kind of sleep disorder. And that's where we're going to focus in the next steps. So here's just our group. So it's led by Professor Martin De Vos. I'm a postdoc there, and who is also a postdoc. Martin also works with REM behavioral disorders. He's a diffuse student. And acknowledge my funding. Thank you.
Thank you. Do we have questions? Here we go. Yeah.
Yeah, this question about the visualization part, this which you have also tried to aware of this pattern method, if you've seen that.
I have seen that there are some recent works on trying to embed the visualization into the network. Is that what you mean? That train the network with some visualization output?
No, it's just another similar technique, but kind of argues that it's more theoretically sound and this is better visualization. But it's
Better net.
Line of method.
Okay, no, I haven't seen it. Okay, thanks.
Yep, we have another one.
When I look at GradCam, it shows you can both propagate positive and negative gradients through a network to look at what goes towards one class and towards negative. If you look at that in an effort to try to make the confusion metrics a little more sharp.
The confusion matrix for the classification task. So I've seen people depicting as blue and red, blue is this part of the signal leads to a positive, correct classification to this class, and a red to negative. I haven't seen them using that into the classification part of it.
Sometimes you can use it to pick up on linear fog, for example, and find some negative instances of when you get N1 versus N2 or something.
Mm-hmm.
Look at the features that it's being confused by and use that to potentially enhance features, since you're kind of using handcrafted, hardly looking things like that. So.
Okay. Even though they're occurring in different timestamps. I mean, like a K-complex might occur in any time of that, and the GradCam would maybe focus on a specific time where this is going to happen.
Right, I think that's very
clear. Yeah.
Right, exactly. Okay. Yeah, shall we take? Yeah, quick one. Yeah, sure. Yeah.
So, the reason you visualize is so that the doctor can look at it and maybe get some insight into why the neural network is saying what it's doing.
Yeah.
Have you talked to medical experts and seen if it both reinforces what they already know and maybe gives them some new insights into sleep?
So I talked with clinicians, and generally they're a bit skeptical overall about this automated sleep station, and they really told me last week that the sleep clinicians, the sleep technicians don't like it much, probably because they aren't great yet. But no, I think it's very difficult for them to understand in this current state. I don't think they will have they will fully understand wavelength transforms and things like that. But maybe if we highlight parts of the signal, for example, if you do an attention and highlight like this part of the signal has led to this classification, for example, of this disease. So we have the whole night of EEG and show a particular part of it, which weights a lot for the classification as having some disease. Then it might be helpful, at least for them to have a second look at it.
I guess there's always still a bit of learning to do between the different disciplines, I guess.
Yes.
Cool. Okay. Yeah. Thank you. Thanks again. So we have the next speaker.
We don't have a
USB, the next small one.
No. What is it called? Maybe someone has in the audience.
The Mac display port to
The old
Mac. The old Mac display port. Anybody have an old Mac display port to HDMI?
Ask technical support.
Otherwise,
All we
just
have
put it
here.
on USB.
Okay. Oh.
That's the VGA?
May not-
VGA too. There's no VGA at all.
There's no,
Okay.
just HDMI.
Yeah.
Okay, so the next speaker is Sheng Zhang, right? And it's about simultaneous measurement implications and outcome predictions for tendon rupture rehabilitation.
Thank you. Sorry, I just used 1 minute to fix the computer, and now I use another minute to read the title. So we do two things: simultaneously impute the missing data, and then we also want to do a healing outcome prediction, and we study the case for Achilles tendon rupture. I'm from Microsoft Research. This is a joint work with KTH and Karolinska Institute. So I'm from machine learning side, so it took me some time to know all these medical terms. But first, I just had to know this is such an important problem. What's Achilles tendon rupture? So in general, it's a sports injury. Your Achilles tendon just like broke like that. That's where it's located. And now we're in Sweden. Just even within Sweden, it's not a big country with a lot of population. Within the 1 decade, there is an increasing of around 20% of patients in Achilles tendon rupture basis. It's based on 27,000 patients in Sweden within a decade. And this is actually a very typical injury because it represents a lot of medical cases. First, it involves a very long healing process, and it may happen, have a lot of complications. And the medical doctors measure a lot of things, but there is still a lack of understanding about the treatment, what's the effect of different factors. Is this better now? I think. Okay. So in general, this is a very important problem, and it's not only important by itself. It also represents a large group of problem from machine learning view because it involves acute medicine, so intensive treatment. Then afterwards, it involves a very long healing process without deep understanding of the factors. Okay, so this is a typical patient journey. So first, the patient got injured, And then the patient commonly very quickly sent to hospitals, and there are some surgery being done. We've got a lot of measurements, like the demographic information, how the surgery is being done, different measurements for blood tests, etc. And then the patient will have a very long healing process with rehabilitations and different exercise. This may last for a year. And then we measure the healing outcome. So the patient may completely recover, but maybe not. So there are some outcome measurements like the ATR scores. So in this work, this is our cohort. This is coming from Karolinska Institute, from the real life patients. This is how the cohort looks like. We have demographic information. We also have different measurements. And in the end, the last two columns, after 12 months, what's the healing outcome? This is ATR score. So we have more than 400 patients collected over the last 5 years, and this data set is still growing. We have 360 variables in total. This is also one of the reasons there is lack of understandings, because medical doctors have different routines and they don't really know which variable is the most effective one, and they sometimes have different understanding on different roles of different factors. And there is a large amount of missing values because in different clinics, there's different routines. So not all the measurements are used. And additionally, some measurements, it's invasive. So you need to implant something from the patient, or some measurements are taken during surgery. So there's 70% of missing values. So as a machine learning researcher, we know like most models are developed for data with complete observations. And with large amount of missing values, what's the traditional way for people to do this is mean imputation or zero imputation and then do the prediction. But with 70% of missing values, this is really hard. So the performance is not really optimal because we're discarding a lot of information. These measurements are not completely independent. So one of the commonly used method is to do matrix factorization-based imputation, so that we assume, like the P, we say it's predictors, we can think about it's all different measurements values, and this is very sparse, and we want to capture the latent trait, which is kind of the patient situation, so we can do mixed refactorization to recover all these missing values. There are different ways to do it. There's more traditional optimization way, and we can also do it in a Bayesian way to do probabilistic matrix factorization. So here we use probabilistic matrix factorization, which is to assume every data entry is independent Gaussian. And so this is a graphic representation for if we just want to impute the missing values. So we assume there is a patient trait U, which is like a number of patients by the latent dimension, and measurement trait, which is the latent dimension by the number of measurements we're looking at. And then we got all the measurements. And for prediction, of course, it is highly nonlinear, and we use a neural network, and we use a Bayesian neural network, and those priors on it. And in the end, we can predict the healing outcome. One way is to use imputed matrix, because that's all the predictors we can have. And another way is for the matrix factorization, what's the latent trait mean? It is capturing the patient healthy situation in that domain. It is representation of the patient status in the low dimension, so we can also do prediction based on this patient trait. So in the end, we're designing an end-to-end model. This is two choices. One is using all the measurements to do the prediction. One is using the patient trait. So for the upper part, this is a matrix factorization model that imputes all the missing values, and then we do it end-to-end to use the Bayesian neural network. So in the experiment, we use two latent layers to predict the healing outcome, the final outcome of the patient. And so this is summarized. So we have incomplete patient information as input. Then we go to an end-to-end model, which is matrix factorization plus the Bayesian neural network. And then we want to complete the patient information and also predict the healing outcome. And this is our result. So we compared, first it's like a standard mean imputation. So we use mean imputation to impute all the missing values. And then we run through Bayesian neural network. That's the first row. And then we also compared with running such method in two stages. If we don't do it end-to-end, if we use a standard matrix factorization to impute value, and then use another predictors. So if we are not doing it to end-to-end, that's the row second and row third. And in the end, that's the two rows using our model if we train end-to-end from beginning, because our value imputation already taken into account about the prediction task in the first place. So we can see that we got the best performance is in this end-to-end model because it takes advantage of a smart missing value imputation. We capture the true patient state. At the same time, the imputation have taken into the prediction task into account. And what does it mean? So I presented this result, and people ask me what does 0.15 mean. So I talked with medical doctors. So in the score, so they don't differ the outcome within 0.1. So if we reach within 0.1, that's perfect. So that's they treat all these patients have the same healing outcome. And now we're very close to 0.1, and we hope we get there soon with more data and maybe with smarter model design. And we also, because we censor the patient all the time, so we actually have the healing outcome score in 3 months, 6 months, and 12 months. So we can put these mid-stage scores either as predictors or as healing outcome, the score to predict. So if we use more measurements, for example, if we stand at month 6 to predict month 12, we will get like higher and higher score because we got more information about the healing process. So we also did experiment in this way to use different predictors. Different time points, 3 months, 6 months, and 12 months. And of course, the best result is using 6 months information to predict the 12 months. Then we got 0.14. So in summary, we have a end-to-end model to impute missing values and predict the rehabilitation scores for ATR patients. And we can show our model works better than our traditional method in this end-to-end manner. And in the future work, of course, when we present our result to medical doctors, we want to know how these decisions are made, which feature is the most important ones. And of course, we show them correlation, but correlation does not indicate causality, right? So we already start to work on how to make our result more interpretable. So at the same time, we just put another paper on archive. So we did causal discovery in the presence of missing data. So we can discover the relationship between all different factors. With such a data set, there's missing data with different missing mechanisms. And then we're working closely with the medical doctors. So our result kind of guides them what kind of next experiment they're going to do. So we're doing controlled experiments based on our result. And at the same time, as I said, this is ATR patient, but it's the same with, like, for example, ICU patient. You go to the hospital, there is acute treatment, but then there's a very long healing process. So this is very representative. So we also want to work with like other medical doctors, with patients from other medical conditions, and improve our model on different tasks. Thank you.
So this was also work done with Karolinska Institute, I guess. So yeah, okay. So it's good to know. We need to go to international conference to know that we actually working next door, I guess. Okay. Are there any questions? Quick questions, perhaps. No, nothing obvious. Okay. Oh, maybe one. Yes.
Do you compare the value imputation towards other kind of methods besides imputation by mean or what any other more advanced methods?
I mean, advanced method commonly like there is this more traditional metric factorization based like of statistical like it's in general like the missing value imputation traditionally all advanced or tensor factorization metric factorization based how to optimize is different. So that's the reason we put it as two-stage model. So that's represent like have a smart imputation and then do a prediction in 2 stage. But I think it's definitely worth tracking more results. But at the same time, so we're actually doing that, but we also see research coming up in actually last months, how to do imputation using variation autoencoders and this type of work. So I think beyond matrix factorization, how to do imputation in a nonlinear manner, it's also interesting research topic.
Great. Okay, thanks. Yeah, I think we'll leave it there. Thank you. So could I ask the next speaker to come on stage? Okay. Okay, and out of interest, I would like to ask the audience, so how many of you actually consider yourself being more, having a technical background, coming from AI, machine learning, knowledge representation, agents? So how many of you are in that field? Hands up. Okay, so it's a good 80% or so. And how many of you have a medical background or a healthcare background or any of that sort? Okay, so about 10 people, yeah, okay, 20 people, 20%, yeah, okay, interesting. So always one of those, I think it's good, it's encouraging. I have been in AI conferences where physiologists or healthcare, people with a healthcare background was actually that was close to none, so it's very good. Okay, so. Andrew, I think we may not have this laptop going. Shall we use yours again? Or yours? Okay. We have two. Oh, we have the second laptop. Yeah, and the next talk will then be by Matthias Hüser. Is that correct? Predicting circulatory system deterioration in intensive care unit patients. I think it is this module that seems to be very advanced. Maybe we need yours after one, yeah. Maybe another quick question. I'm just now curious. I have you all in front of me, and that may take another half minute or so. But how many have been working in the field of AI in health and medicine for, let's say, more than 3 years? How many have done that? More than 5 years? More than 10 years? Okay, so like, okay, 20%? Okay. And the rest recently, I assume, within the last 3 years or so. Okay. And who's intending to come tomorrow, to tomorrow morning's session, in the panel and so on? Okay, most of us. Good. Excellent. What's that? We don't. Which one do you need? This most recent one. Most recent. I have no idea. Nope. I can ask the technician easily. We actually have the last speaker in the room too, actually, yeah. I wonder one alternative is if this takes a little longer is to have you in first. And then you can switch.
Yeah, maybe the different adapter.
Yeah.
So, yeah. You want to
maybe we do that. And we can get there. Yeah. So Matthias will then speak in about 10 minutes or so. Last speaker, that's Marcel Bjerke, is that correct? From Lübeck in Germany. And it's towards lifted maximum expected utility. And if you're lucky, it may just work.
Yeah, it looks good.
Looks good? Excellent. Great.
There we go. Okay, so today I'm going to talk about online planning by calculating the maximum expected utility. And we don't just want to calculate the maximum expected utility for each patient individually, but for groups of patients, which is the lifting component. So I'm going to present the lifted maximum expected utility. So let us first start, why do we want to calculate decisions for groups of patients instead of doing it individual for all patients. So what we can see here is a little example. This model on the right-hand side can be used, for example, to reason whether a patient retains water. So we take the change in the weight of a patient, and based on some probabilities, we say this person retains water or not. And to improve our predictions, we also consider the persons with whom they live together. So if both of them eat quite a lot, they will both have the change in their weight and therefore not retain water. What we can see here is that this is modeled for 3 patients, and each patient is modeled individually, and the model grows exponentially in the size of our patients, which isn't really good. But what we can see here is that there are patterns which, or that all of them behave identically. So there are repeated structures. And as I said, we want to do some kind of decision-making support. So we have a temporal aspect of too far actually in there, and now it's looking even worse, right? So we have now 3 patients and 3 time steps. Imagine this for millions of patients and, well, a lot of more time steps. But the good thing is we have there repetitive structures in there. So I said already for 1 time step, each patient more or less behaves the same, and they also behave the same over time. So we can come up with a more neat representation for this. So what we did here is the same model, just basically lifted. So we have now not each patient modeled individually, but have variables as representation for whole groups of patients. And what we have here is now on the very left-hand side, we see, or right-hand side, we see that we can observe the change of weight, and that this has an influence to the condition of patient, and also that the condition of patients has or is related to the living together variable. And we can also see the temporal pattern, which can now be basically used for all time steps. And this is actually a really good representation to answer single queries. And it's just a compact representation for the local and temporal pattern. And so I said on the beginning that we want to reason somehow. So what are our query types? So we have, for example, prediction how likely is it that my patient retains water in 10 days or 5 days. We have full-time queries, the condition of my patient today, and we have smoothing queries. So how likely was it actually that my patient was healthy 5 days ago? I mean, if you gain more evidence about your patient's new information, you actually know more about how he was in the past than you know back then. So these are our query types. And we have basically worked on algorithms to have multiple queries on these things efficiently, so that we can do this for different patients efficiently by, again, reusing computations. And what we want to do now is to use these representations to also support decision making by calculating maximum expected utility. Therefore, we need to extend this representation with action and utility nodes. So for example, we have action nodes like a doctor to do nothing because our patient is healthy, or if we think the patient isn't healthy anymore but starts to retain water, he has to do something like visit the patient or send a nurse or however the proper translation is, and to really check upon the patient whether he retains water and then do something about it. And obviously, we want to calculate the best action, therefore we need some kind of utility to represent rewards. So obviously one could always just send the doctor to a patient, then you will always be right to detect a water retention only, but this would result in an unnecessary cost. So a doctor also only has a limited time available, can only see a few patients a day. So you need to have basically a trade-off between when do you do one action and when do you do the other action. And this is basically the thing we are suggesting. So we want to have a nice representation where we can reason over patients, and then include actions and utilities in there. And we got questions about, so like this we can reason over groups of patients, and we got questions like, okay, but how do I select the best action for one patient? Or how do I know that I do actually select the right action? This is basically done by, we are always getting evidence from the change in weights. So that we have basically groups of patients which behave the same. And the action is valid for those groups, but the evidence we get basically splits the whole group of our patients into smaller groups, for which we then reason. So it's not always just the whole set, but smaller groups, but it's still way more efficient when doing this for each patient individually. Okay, so what did we propose? We proposed that if you want to do something like online planning or sequential decision making, that you cannot do it for each person individually, as we have some billion people on the planet, and you would have to model this thingy for at least a few thousands if you just concentrate on your city or town. And therefore we suggest that we extend existing lifted temporal representations with action and utility nodes to support lifted maximum expected utility reasoning, and thereby we have an efficient way to calculate best actions for multiple patients directly. What is left to do is to really formally define it. This wasn't done in the paper we sent in, but by now we actually did it. And then to extend our formalism to also handle multiple queries well, which we did already for the part without action and utility nodes. Okay, thank you.
Right. Thank you. Okay. Maybe while we transitioning, we have, if there's a question, Go for it. No? If there's something bubbling up, I'm sure you're available for more questions later. All right, second try. Okay. Okay, Matthias, Lisa will talk.
Yeah, so, first of all, sorry for the delay with the electronics. Today I want to present a joint work between my group at ETH Zurich, the Biomedical Informatics group, and the Inselspital in Bern. And the topic is predicting circulatory system deterioration in ICU patients. And this is joint work with Stephanie Hyland, Shinrei Liu, Martin Faltis, Cristobal Esteban, Tobias Merz, and Gunnar Retsch. And let's get started and look at the problem. So on the left-hand side, you can see a trace of an ICU patient, where in the different rows you can see the channels of the ICU patient. And in this case, the ICU patient will go into a circulatory system deterioration, shown on the shown here. And usually, prior to these deteriorations, there's certain patterns in the signals that we can see. For instance, here, the heart rate of the patient is steadily increasing over the time window about 8 hours before the deterioration, whereas the other channels are not really that meaningful to us. But we hope that if we propose an automated system, then the machine learning model could pick up some patterns, for instance, in these channels here, related to the complexity of the signal or the different the slopes over different horizons. And so the general principle is that we observe some history of the patient, which is taken over all the different channels, and then we are predicting some event which happens in the future. And ideally, we have such a probabilistic score which is increasing in the hours upcoming to the event. So then the deployment scenario in the ICU is like this. We have lots of different monitors, and we want to implement a decision support system for the nurses. So in this system, we are predicting 8 hours ahead, which corresponds to one shift of a nurse in the ICU. Okay, so how do we define circulatory system failure levels? So first we have this stability baseline, and then we define 3 different levels of severity of cardiac system failure. And how we define this endpoint is based on the lab test lactate. So if the patient is in a stable lactate state, so lactate is the most important ingredient of this endpoint. So if the patient is good for the lactate, then he will always be stable. And we have some other ingredients which are depending on the drugs and the mean arterial pressure. So the idea is here that the patient might actually be fine, but might actually be fine because lots of drugs are given to the patient. So this is kind of masking his physiological state. And so we take also into account the drug dosages when defining this endpoint. Okay, so this is just about the current circulatory system state. So what we actually want to do is to predict these deteriorations in the future. And so we could imagine that in this case, at this point in time, the patient will transition between one of the levels that I've introduced in the previous slide. So they might go from level 0 to level 1, or they might go from level 0 to level 2. In this case, we don't make any distinctions between these transitions because after speaking to doctors, they have told us that the most important transition to predict is this transition from stability to any kind of instability, because then the patient will get closer attention. So technically, this works by having a floating window. So if the deterioration event would be happening here, then the alarm would sound just when this rolling window would hit. This rolling window of size 8 hours would hit this deterioration event here. The alarm would first sound at this time point. Okay, so the model development data consists of data we've extracted from the database management system of the Inselspital in Bern. So it consists of 55,000 patients, which were then reduced to 44,000 after some applying cohort selection criteria. Then the feature selection was done by consulting the clinicians about which of the channels are clinically relevant. And also we wanted to select channels or observations which are commonly measured or observed in the ICU to make the system transferable to a different intensive care unit. And then a very important step was also this feature merging, which you can see here. So there we reduced the number of variables from 700 to 200. And the idea is that many variables have similar meaning, but they have just different names in the DBMS. So we just merge these variables together to give something semantically meaningful, which we then also can interpret. The model can be interpreted better in this fashion. So the different variable types that we've used consist of monitored values, which are coming at regular intervals, but we also had pharmaceutical, which we have converted to doses onto a time grid so that our model can process this data. And also we have here lab test measurements on the bottom, also observations. So the overview of the processing pipeline is, so after we've extracted the data from the DBMS, we then performed these variable selection steps, cohort selection steps. We then converted this into these semantically meaningful variables. And then we had some data imputation step where we put the data onto a time grid so that it can be processed by our machine learning model. We then defined the endpoints, and we have done a feature construction step here, which allows us to use models like logistic regression or let's say gradient boosting methods, which do not have these recurrent updates like an RNN. Okay, so I want to give you a bit more detail about the feature construction. So our features consist of 3 different types. So first we have extracted the static variables of the patient, which are given at the beginning of the stay, which could be the age of the patient, the sex, or different diagnosis groups. Then we have these features which are about the short-term history of the signals, where we are taking different windows over the history at different scales. And then we have defining these 5-point summaries, so we can look at the slope of a particular channel over the history, can look at the instability of that channel over the history, and this allows us to capture all kinds of trends in the signals, and this was done in close consultation with the doctors. And then we also introduced these entire history features because we noticed that these give us a good idea how the patient is generally doing. So how this works is that we look at what fraction of time the patient has stayed in a particular of these states that I've introduced in the first slide. And yeah, this gives us a baseline of instability. And if we take all of these features together, we then reach a training data set size of about 2 million samples and 2,900 variables. So the experimental design is motivated by the standard use case of such a model, where we develop the model on data that is from the past, and then we deploy it on future patients. And so we have defined these different splits. And for the results that I want to show today, we only looked at this particular split here. And we also had these held out sets, which we will not use at all, except in the final application. Okay, so for the results, the prediction performance of our model is generally really high. So we achieve an ROC of 0.94. And a more important metric in this setting, however, is the precision recall curve, because we are dealing with a rare event. So the prevalence of this event is about 5%. So, but even on the AUPSC curve, we can see that we have relatively high recalls, which is relevant in the ICU. We have precisions of about 40% with our model, which is comparable to other models, other alarm models for the intensive care unit. And we also tried different machine learning models, and we can see that it was indeed valuable to use nonlinear methods, gradient boosting, compared to the logistic regression. We can see that there's a quite significant increase in the performance. On the previous slide, these AUPSC curves are still hiding some details that are really relevant in the ICU. So we analyzed in detail also the false alarm rate behavior of the system. So this mimics the scenario in the ICU where we are picking some particular decision threshold, which is here denoted by tau, and then we're fixing that threshold then, and then we can analyze for given events which are before the deterioration, we can analyze how many of these events are retrieved conditional on how many minutes before these events, these segments are happening. And so we can see that for false alarm rates of about 50%, so it's defined as 1, the precision is 1 minus the false alarm rate, we can see that we achieve, like recalls which are, like 50% here. And you can see that the model works obviously much better if we are closer to the deterioration event. And then our most recent step was that we wanted to build a parsimonious model, which means that we want to have a model which only uses few variables. So we analyzed the feature importances, and we consulted with the doctors, and they indeed told us that those are important variables that would define the endpoint. And also it was encouraging to see that different types of variables were selected. So we have some static variables, we have medications, we have vital signs, so it was indeed useful to use the different variable types. And we can see that our model, the full model, which you can see here, compared to the model which has been reduced to the top 20 variables, there's indeed almost no difference. So this is very helpful for the future external validation, because then we can go to the clinician and say, we only need these commonly measured variables, and we're going to externally validate this model for a different hospital. So in conclusion, we have presented a dynamic risk score for cardiac system deterioration, which achieves a performance of an area under the PRC curve of about 0.54. And we have also shown that we could build a parsimonious model using only the top 20 variable, which will much simplify the validation, the external validation of the model, and also the deployment of the model in the intensive care unit. And in future work, we also want to look at more complex machine learning architectures, which allow more efficient processing of this data. Yeah. Thank you.
Great. Thank you. So are there any burning questions? We're a little bit over. Yeah?
Yeah, so you're predicting L0 to any one of L1, 2, 3. Yeah. So the thing I'm confused about is how you define this L2 and L3 based on dose of vasopressors like noradrenaline or whatever. And then your most important features are also the dose of noradrenaline and whatnot. So how is that working, that you're presumably they're not on any vasopressors and then they start vasopressors 8 hours later, but your most important feature is the dose of the vasopressor?
Yeah, I mean, it could just be the absence of any, it doesn't mean that it has to be present.
I just don't know how people are in L0, you know what I mean? Like, it's the definition of your L2, so I don't know how it's useful in predicting L0 to like L2.
Yeah, so these feature importances, they were pooled over all the possible transitions, and it doesn't mean that for a particular of those transitions, so we can have the possible transitions 0 to 1, 0 to 2, 0 to 3. We have not analyzed here which of those transitions these are important. We just pool over all the possible transitions, and then we have just seen that those are the most important variables.
Okay.
Can I suggest, I think I know the gist of your question, actually. It was also a little unclear. But good opportunity now to maybe get in touch and talk about it. This was the last talk, so thanks again. Good. And then just 2 or 3 things. I keep it short. I know the lunch break has started already 7 minutes ago, but there will be plenary sessions now at 1:30. That means that during the time from 1:30 to 4 p.m. we will not have sessions here, but we start again and reconvene at 4 p.m. from 4 p.m. to 5:40 p.m. And that is when Andrew Costa will actually take over the chairing of those types of sessions. Or Isabel, exactly, one of other co-organizers. Is there anything else, Andrew, that we should mention now? No? Okay, fantastic. I hope you enjoyed the first 2 sessions, and I see you soon.
If you don't want to go for lunch in here, then
lunch.
on the other side of the train station, there is a subway and a walk and a supermarket. and they get very busy very quickly. So
Yeah, exactly.
that's about your options,
Yeah.
there or there.
Yeah, exactly. Thank you for coming.
Hi. Oh, pleased to meet you.